And first, I want to thank the Organizational Committee for invitation to the Medical Neurobiology 2017. Okay. This year, in memory of Evgeny Vasilievich, and the possibility to have talk here, which is, I'm glad to present it to you, attention entitled Conformational Variability of APP mutant transmembrane fragments can be associated with the initial steps of Alzheimer disease development. First of all, I want to remind you that the APP have a structural similarity to the type 1 receptors. That receptors have only one transmembrane domain, and the APP have the cleavage of the full-length APP by alpha, beta, and gamma secretases releases soluble actor and intradomains, as well as A-beta peptides of different length. And the APP have a conserved motifs, domains, E1, E2, Kunitz domain, acidic domain, heparin binding site, phosphorylation site inside the cells, G protein coupling sites, internalization site, and caspase cleavage motif. So that's receptor, definitely. So because of its multiple cleavage sites and the fragment produced, it's difficult to understand the true function of the APP, and as well as alteration of its function and other malfunction than Alzheimer's disease, for example. And amyloid cascade hypothesis assumes not only plaque formation, but also neurotoxic effect before the plaque formation by the alteration and function of membrane itself, and leakage of water and ions, and the forming of the pore and uncontrolled ion channels. And here we see the picture of the APP processing in terms of amino acid sequence. And CE99 usually sequentially processed to the proteins over a length, having length from 38 to 43. Of course, most widespread isoforms are A-beta 42 and A-beta 40. The ratio between them is lower than normal and increases significantly during the pathology, causing the plaque formation. But at the same time, it was shown that the A-beta peptides is a representative of the innate immune system of brain and may act as antimicrobial peptide. That is why all strategies that aimed at the depletion of the A-beta peptides during the at least the beginning of the Alzheimer's disease may cause severe consequences. And the aim of our study was to resolve the special structure and conformational rearrangement of APP transmembrane fragment, containing or not metal binding site, metal chelating domain by heteronuclear NMR spectroscopy, of course, in the membrane mimicking environment. For the purpose, we constructed we obtained these fragments in bacteria, in cell-free systems. Of course, for the structural investigation, it should be isotopically labeled. And the selection of the medium is of great importance. The surrounding of imitating the natural surrounding of the object is of great importance for all structural investigations. Both detergent micelles and lipid bicelles were used for these investigations. And here's the best results we obtained in DPC, totally due to raised DPC micelles. And at ratio 1 to 40, PD protein detergent ratio 1 to 40, which corresponds to the more than one molecule of protein per one micelle. We see the peak splitting doubling corresponding to the monomer dimer transition. And when we increase the concentration up to 1 to 30, the population of the dimers increased significantly, and the protein peptide, the precipitation of the peptide occurs in 1 hour. So this is a very difficult object to investigate. And from obtained NMR data, it is clear that APP transmembrane fragment hour have two transmembrane, two helix regions. One of them is totally transmembrane segments. Here you see the positive chemical shifts from C-alpha atoms, and nascent juxtamembrane helix. In the middle of this transmembrane helix, we see the periodicity of the amide protons chemical shifts. It means that here in the approximately in the middle of the transmembrane helix, here is some periodicity in hydrogen bonding, so it forms the slight kink with a 50 degrees angle. So I will not bother you with the structural data anymore. And the dimerization was confirmed by analysis of noise spectrum and reveals characteristic noise contacts. 6 of them were assigned ambiguously. Here we see the superposition of 10 structures of the backbone atoms. They match perfectly, and here's the mobile loop. And if we introduce this small gap in this loop, we will see that the perfect matches the composition of the juxtahelix fragment helix too. So the distance between this dimer helices is 8.3 angstroms. The average angle is 35 degrees. Average because of the kink on the N-terminal part it's 60 degrees, and C-terminal part is 26 degrees. And the hydrophobic and hydrophilic properties of the APP transmembrane domain dimer interface are presented according to the molecular hydrophobicity potential and cylindrical coordinates here. This interaction area indicated by violet dot, this area pretty big, it's 630 square angstroms. And pay attention that 5 mutations are situated at this surface. In DPC micelles, this dimer associate via heptade dimerization motif and form left-handed dimer, which is a very typical form for heptade dimerization motif. But to go back, we see also that on the opposite side of this helix, there is unemployed GG4 motif. And if we would see dimerization on this motif, it should be right-handed parallel dimer, and it was shown by solid-state NMR scientists. It's another fragment, another APP fragment, but it's still APP, and they saw the dimerization via GG4 motif in there. It was found in DPC, DMPG liposomes. And recent cross-grave MD simulation study elicit the role of the membrane lipid composition in conformational rearrangement of the APP structure. Different lipids favor different protein conformation population in the B layer. So this supports the hypothesis that the change in membrane composition results in change in water permeability, lipid ordering, and may have a significant impact of the membrane proteins structure, interaction, and then of course function. And the lipid bilayer promote different conformational state of APP transmembrane domain, and the dimerization via GG4 motif were found in solid state studies, the dimerization of the heptad and terminal motif were found by us, but in solution in NMR in mice cells. And these structural alternatives suggested by different arrays of the experimental data are not necessarily mutually exclusive, because they both dimerization motif can be functionally relevant in different circumstances that occur in membrane. And shortly we have our own MD simulation, the interaction of holsterol with the transmembrane fragment, both in mice cells and in bi cells. Shortly, I would say that this interaction may interfere, compete for protein-protein interactions. And thus, both dimerization motifs existed in APP domain, were found by molecular modeling and confirmed by biochemical studies. Tetrad repeat motif was shown experimentally by solid-state NMR, and dimerization via heptad repeat motif was shown by liquid NMR. In this case, in the case of dimerization via heptad motifs, cholesterol can bind this glycine pocket and compete with the hinge between these two conformations. And pay attention that 5 familiar mutations situated here in the contact interface. And the most interesting that there are even leucine 723 mutations to proline. It's Australian familial mutation causing Alzheimer or early onset of the Alzheimer disease, still capable to cause the disease. So we paid out attention to the 3 mutations on the C-terminal part of APP transmembrane domain, and investigated also 2 truncated forms corresponding to the numeration of A beta. It's 1549 and 1546. Glycine and isoleucine mutants retain the alpha helical structure as well as wild-type peptide, and remain stable for weeks unless their proline mutants demonstrate the same behavior as truncated constructs. They're very hard to investigate because of the high aggregational propensity. They obviously undergo the conformational transition from alpha helical form to the still soluble beta oligomers. And the hallmark of this transition is of course, the peak broadening and shifting to the 9 to even 10 ppms. And before the beta structural transition, truncated fragments still retain the alpha helical conformation and remain embedded into the micelle. And here's the most interesting part. It is there for proline mutant. We found that C-terminal part of the transmembrane domain undergo distinct helix unfolding. Here we see the disappearing of the positive positive chemical shifts from C-alpha signals, and increased water exchange. That is very significant subject, because it may facilitate the gamma secretase cleavage, because the cleavage of the E beta peptides by gamma secretase active sites is situated to the 5 angstroms from the from the inner surface of the membrane. So, and at the same time, we see the significant decrease in water exchange for lysine, glycine, and alanine. It means that the transmembrane, that the C-terminal parts snorkeling or embedded inside the membrane, and that's a very important issue, because now we can see, I can say that we are the first group that see the experimental evidence of this process, because everyone have it in mind, but no one see that. And of course, it's very interesting data. It will be published soon. And a little bit to announce our future investigation. So the great progress has been achieved in recent years in the field of gamma secretase structural study, and in 2015 Bioorganic reported the improved cryo-EM structure of the gamma secretase complex composed of all 4 proteins. The complex have 20 transmembrane domains, and if we will make the section across and within membrane, we will reveal the horseshoe shape. And here is the 2 aspartate residues forming active sites from presenylene transmembrane segments 6 and 7. And there is it was proposed several modes of the APP recruiting to their active site of gamma secretase. One of the is from the concave site nearby the transmembrane domain 8 of presenylene 1, and another from the convex site nearby the transmembrane segment 2. And for the purpose to investigate this interaction, we made a construct and obtained the gamma secretase transmembrane domain 8 from presenylene. Sorry, here's a pointer and the slide shifting so close to each other. So if we have labeled APPTM, where in this spectra we have all amino acids assigned, we see the definite peak doubling and shift. That means that these 2 molecules interact with each other. And in the opposite spectrum, where we don't have the assignment for transmembrane domain 8 yet, we see the same changes. So this model system will be for investigation of the influence of the APP transmembrane mutations. Also may shed the light to the APP processing. And thank you for your attention. I want to thank my colleagues, Anatoly Urban, Kirill Nadezhdin, Eduard Bocharov from NMR group, sharing the protein expression, and Pavel Valinsky, who is responsible for MD simulation. Thank you for your attention.
Thank you very much. Questions? Please, Viktor Ivanovich.
Well, sir, thanks a lot for excellent presentation, really excellent work. And are you planning now to compare the structure of your fragments, which you so accurately determined, with the amount and the character of the peptides cleaved? Do you have such possibilities?
What do you mean?
I mean that you say that the structure, and you were lucky to have some well-known mutations within your transmembrane fragment. Am I correct? Or absolutely incorrect?
No, we have investigated only 3 mutations, but we have a plan, C-terminal part. But we have a plan to investigate the another membrane regions. And of course, we haven't calculated structure for this mutant yet.
Well, so I misunderstood apparently, and I approach you later. Thanks.
Yeah, we'd also like to thank you very much for your excellent presentation. The peptide you use for NMR studies resembles rather the alpha CTF generated by alpha secretase, a bit longer.
Yep.
So do you consider that there's any difference between the alpha CTF and the beta CTF regarding your structure or the dimerization behavior of both CTFs?
C-terminal fragment, you mean?
Yeah, I mean, you use the alpha CTF generated by alpha secretase, a bit longer, 1 or 2 amino acids. But then there's an alternative for amyloid products. You have the beta CTF, which is longer.
Yes.
Is there any difference in this behavior, or did you test this?
You know, we have that. I showed in the beginning that We called it APP fragment, transmembrane fragment with metal chelating site. So we have investigated its behavior and but do not have a structure because it aggregates I don't know why. Even in the absence of the metal ions, it aggregates much at lesser concentration than if we have a peptide with cleaved without this metal binding domain.
Thank you.
It's hard to obtain the structure if you do not have a time for spectrum acquisition.
Okay, it's time to go further. Let's thank again the speaker.